Hello, my name is Ivan Tomac, and this is a video presentation of the research on modal identification using Morlet-wave integral, published in Mechanical Systems and Signal Processing. Video presentation is organized in the following way. It starts with the motivation for development of a new method, which is introduced by highlighting its main features. The method is then explained through demonstration of the developed Morlet-wave modal package, which is first introduced. Then, basic usage of the package is demonstrated on a simple example. And then, parameters of the method are explained. The presentation ends by performing modal identification on the experimental example from the manuscript. Method is developed primarily for modal identification from short, noisy, and low dynamic range signals. An example of such signal can be seen in time domain and in frequency domain. Identification is performed in time domain from the free response signal. The method is based on the continuous wavelet transform, and because of this, the whole signal length is not required for modal identification. Overdetermination is introduced to reduce uncertainty by performing identification at multiple time indices using least square optimization. Method is ready to use via developed Morlet-wave modal Python package, which source code is available on the GitHub. This package is developed under the MIT license and is installed using a pip package manager. This is a recommendation for importing it into the code. For the basic usage, method requires free response signal, its sampling rate, and initial natural frequency. Identification starts with initializing object identifier by calling a class Morlet-wave modal. The free response and its sampling rate are set. Modal parameters are identified by calling the wrapper method identify modal parameters, which requires initial natural frequency. Method returns modal parameters in the following order. Basic usage is demonstrated on the synthesized single degree of freedom system response. So first the response has to be created, which starts with definition of time domain. Then a response of single degree of freedom mechanical system is generated using these parameters. Some normal distributed noise is added too, and this is a resulting time series. So object identifier is initialized by calling a class Morlet-wave modal. Next method is called where the natural frequency is provided. So theoretical value is slightly increased to emulate picking from magnitude plot in frequency domain. And we initialize identification. And now we can go to the results. And here we have theoretical and identified results, and as expected, they look fine. Now a few details on the parameters of the Morlet integral are explained. In addition to required inputs in the class, there are additional arguments that are set as default. These are the parameters of the method. So, the first parameters are not to be changed if the system has damping ratio between 0.2% and 2%. Going above 2% damping, they should be set to 6 and 12 or even 7, 14 for higher damping. The second parameter sets the minimal length of the signal taken for the analysis. This value can be increased at low damping ratios or close modes to these values, or reduced down to 5 oscillation in case of damping above 2%. The third parameter is related to number of equations that are used for identification of the modal parameters using the least square optimizer. Reducing it improves performances at the cost of uncertainty. Upper limit of the analyzed signal is set to maximum of 400 oscillation. It can be adjusted via wrapper method through the damping estimated parameter, which is set by default on 0.25%, which results in maximum 400 oscillations. Damping estimated is related to number of oscillations via this expression. It defines maximum theoretical length of the Morlet wave function for selected damping ratio. So, the expected length of the response for different values of the damping estimated can be seen on these plots. For example, the maximum signal length for the expected damping of 2% is 49 oscillation, and it goes down to maximum of 400 oscillation for default value of damping estimate. More details on this topic are provided in the article. Setting this number is useful when damping is higher than 0.2% to limit the length of the signal taken into the analysis. Modal identification is demonstrated on the experimental example from the manuscript. It's a steel beam, and here is the experimental setup. It is excited with a single impact of the modal hammer at the location of the accelerometer. So, first, experimental data are loaded, and important parameters about the signal are extracted. Next, frequency response function is generated calling a special function getRef. Next, the frequency axis is generated, and we limit it to a certain range of frequencies. This is required for picking natural frequencies from the magnitude plot, which can be seen here, and then we pick natural frequencies using a special function here, and there they are. Now, array to store modal parameter is initialized, and also array store k-limit used for each mode, which is required to calculate maximal signal length for the identification. Identification is performed on the impulse response function like in the article, which is obtained using the special function. Now the modal identification can be performed using this simple code. So here we see initialization of the object identifier, and k-low is increased because of low damping. Then the wrapper method is iterated over selected modes. And now we can plot the results. First, we have results of natural frequencies. Then we show the results of damping ratios, amplitude, and phase. Here, the total length of the signal required for the identification at each mode is shown. It is obtained by simply dividing the maximum k-limit used for each mode with the corresponding natural frequency. So these are the k-limits used for each mode, and these are the lengths of the signal used for identification. And with this, demonstration is concluded. This work is done under the EU project Nostradamus, which is funded by the European Commission. Thank you for watching this video. If you like it, please press the like button below. Thank you.